Hello.
Hello, everyone.
Yeah, I can hear you.
On Zoom, can you hear me?
Yes, we can.
Okay, thank you. Okay, I will start the lecture. Today's lecture is about file systems, and we will talk about how these file systems are organized in the operating system, and especially Linux operating system. Okay. Okay, so why we need a file system? So as you can see that essential requirements for long-term information storage, when you turn off your computer, so you need the information to be stored, to be kept, okay? So you don't need to lose any information after you turn off your operating system or your computer. So that's why we need some file system in order to organize our files. So you can think of the file system as a linear sequence of fixed size blocks. And as you remember from the previous lectures that we have some blocks in the memory. As these blocks are, we have fixed size blocks, and these blocks, we read them or write them. So there's two operations, which is reading the block or writing the block. Okay, so the questions here that maybe you can think of these, how do you find this information? Because here we are thinking of that we have a disk. You have HDD, not SSD, because it's different, right? So how do you find this information? So you have to, this driver should find the block which belongs to the file in order to read the file. Or if you would like to write on the file, so you have to find empty blocks so you can write on them, right? So you have to search for these blocks in the disk. How do you keep one user from reading another user's data? So you need something like user management, right? So you can create users, you can create groups of users, you can give permissions. For example, you have a file, you don't want to give, you are the owner, you don't want to give permission to another user to use this file or to access or to read or write. So you have a set of permissions that could be given to the files and also directories. And how do you keep which blocks are free? How do you know, sorry, which blocks are free? And this is a job of operating system, right? Because here, if you look at the memory or the disk size, so you will see it's free, so you can write fast, but you don't know where it's written in the disk. Maybe it's in a contiguous order, maybe it's not, maybe it's random, right? Because if the operating system find free blocks, so it will write them. It will not find contiguous blocks, it will write them not in order, right? And there's another operation which is called a defragment. We will talk about them in the last slide, okay? Okay, what are files? So you can think of files are logical units of information created by processes, okay? So you remember processes, and you can run, create a process by running a program, and this process can write files or read files. So you can keep information in files. So these are how the file system works and how the operating system manages this process. A disk will usually contain thousands or even millions, yes, because they are very big sized disks, okay? Typically files have a name and extension, and you know all of this information, right? If you look at the file, you will see a name and extension, but in the back side, there's many things. There's metadata, there's something like called inode. There's, for example, blocks of the data where it's stored in the disk, right? But if you look at the file, you will see only name and extension. And here are some extensions examples from the textbook. And here how the file could be structured. So we have three kinds of files. So we have byte sequence, and we have record sequence, and we have three structure. And you are familiar with tree structure, right? So here you can see that maybe one folder contains many files, and yes, and another folder contains other files or maybe folders. And you are familiar, I think, with this kind of file system. Okay, so here, the first one, which is about byte sequence. So here we have unstructured sequence of bytes. Yes, and both Unix and Windows use this approach. So here, how the file is stored in the disk. So we are not talking about how it's organized, because here in Unix, for example, we have something like called inodes. Okay, and these inodes, it's something like it's unique for the file, and you can create hard links or simple links, and you will see them in the lab. A sequence of fixed links records, each with some internal structure, and the third one, which consists of a tree of records, not necessarily all the same lengths, each containing a key field in a fixed position in the record. The tree is sorted on the key field to allow rapid searching for a particular key. So here, how the files are organized in the disk, okay? So we have three kinds. About file types, so we have here regular files are the ones that contain user information, and we have directories. So you know the directories or folders are system files for maintaining the structure of the file system. Because here, for example, if you create a group of people, so you will see a file which is stored as a groups of these operating system, for example. Character special files are related to I/O and used to model serial I/O devices such as terminals, printers, and networks. And block special files are used to model disks. So we have 4 types of files. Yes, and here, and you can see that how could be the structure of the file. For example, there is a header, there's a text, data, and some bits for relocation and for other things. And maybe it's other kind of file, which is archive. And here you can see different kinds of blocks. Okay, so regular files are generally either ASCII files or binary files. So you know that ASCII files, we mean the text files, and binary files, it's binary 0, 1, okay? ASCII files consist of lines of text. Okay, in each line is terminated by carriage return character. In others, the line feed character is used. So it depends on the operating system. Binary files have internal structure known to programs that use them. And if you try to read their binary file, you will see something strange. You cannot read it as a text file because it's binary. You can't execute it. A simple executable binary file taken from an early version has 5 sections, for example: header, text, data, relocation, bits, and symbol table. Second example of a binary file is an archive, also from Linux. So as I showed you in the previous slide. So we have sequential access. What do we mean by sequential access? Any answer? Yes, so we are reading the bytes one by one, yes. So in these systems, a process could read all the bytes or records in a file in order, starting at the beginning, but could not skip around and read them out of order. So we have to read the file sequentially, because if you store something in the line 5 and you read it after you store it and you read it, you see that it's in the line 6, so there's a problem, right? So we have to access the file sequentially. And there's random access, and the random access, so you know here, that records could not be in contiguous order, right? As I told you, because here you may not find contiguous blocks to store your data. So it could be something like stored randomly. And here you may need random access, right? And here we have in this modern operating system, we have random access. And in the past, there were something like sequential access. Yes, and here we have some attributes for the file. For example, we have some attribute for protection. So who can access this file? And but if you look at, for example, Linux operating system, you will see only three kinds of permissions, right? Read and write and execute. And you can change it, or you can disable it, enable it, and you have three classes of people, so that you can give them these permissions. For example, owner is a group and the other, right? And we will emphasize it in the lab. Okay, so what can I do with the file? Okay, I can create a file, delete file, open, close. So when you open the file, what you're doing, you are reading the file, right? And when you close it, so okay, for example, I edited something in the file and I closed it. Read the file, right? Okay, I think you know all of these operations. But here the idea is, how can we do it in the code, right? But here we will not cover the code, only what kind of operations exist. Okay, there's, for example, append. You know append? How can we append in terminal? For example, you have a text, you want to append it. What was the meaning of append? Append is something like you add some text, okay? You write some text to the file without editing or without removing the content, the previous content of the file, okay? This is append. Seek, which is about reading, before reading, so you have to seek for blocks of the file. Get attributes, set attributes, rename. Yes, because here we have different kinds of attributes, so you can something like get and set attributes, and you will see them in the lab more practical. Okay, what about directories? What's the question? Yes. The renaming, it's not name, it's not one of the attributes, because here there's a name, for example, in Linux, it's hard link to the file, because here the files are stored as inodes. Okay, and when you give a name, for example, when you create a file, you are giving a hard link to the file. Okay, so when you create a new file, so you have inode in the operating system, sorry, in the file system, and you have a hard link to this file. You can create other hard links, but so the name is not one of the attributes. What we mean by attributes, so something that you can change, for example, permission of the file, something that you can change one of the bits, for example, the file is in a read mode or write mode, okay? Yes. Okay, so we need directories to organize these files better, I think, because it's not better to store all of the files in the same folder. Okay, so here we have a very known kind of organization of the files. For example, here we have one directory which has 4 files. And here, for example, we have a hierarchy of directories. And here you can see that we have directories, and inside the directories, there are other directories. For example, here, as you can see, the square refers to a directory, but the circle refers to a file, right? Okay, so path names, so we have two kinds of path names. We have absolute path name and relative path name. And you know all of this. Absolute path name, it begins from the root directory. Okay, so for example, if you have something like, okay, so for example, user, home, you have here some file.txt. So as you can see here we have, for example, some relative directory, and here we have the absolute directory. So absolute directory, it begins from the root directory, right? Yes, this is the main difference between absolute and relative. Okay. Okay, so structure of path names. So these path names are taken from Linux operating system. So as you can see, so we have a root directory which begins with this slash forward slash. Okay. This called forward slash or root directory. And here you have, for example, this directory, this a directory, and this a file. Okay. Or you can say that this is a subdirectory. Okay, what kind of operation can we do with the directory? Okay, we can create a new directory, delete directory, open some directory, and close the directory. And you will see that we have the same kind of permissions, RWX or read, write, execute, but it's interpreted differently in case of directories. Okay. Okay, so here we have, for example, link. So why we don't have links to the file? We have link to the directory because of circular linking, right? So if you link to the same folders, there will be a problem because here you will see it in the lab. So when we create a hard link, we cannot, in case of directory, we can for the file, but in case of directory, we can create only symbol link. Okay. Okay, so here we have file systems are stored on disks. Yes, most disks can be divided up into one or more partitions with independent file systems on each partition. For example, if you look at your file system, you can see, for example, some area, it's called the swap area. So there's a file system, you can divide these into partitions, and you can define different format for each partition, okay? But it may need it or not, it depends on the operating system. Okay. For example, here we have some file system layout. Okay, so here we have, for example, MBR block. After that, we have some partition table. So how these partitions are, I mean, how it's organized. And we have here boot block, super block, free space management, inodes, and root directories. So here, as I told you, the inodes, which are files in fact, okay? But when you give a name to the inode, it becomes hard link to the inode, okay? And we have root directory and files and directories. So we have some files or some blocks which are required for running the operating system and managing all of these processes. Yes. Inode is index node. Yes, and inode it is an actual file. So when you create a file, you are creating an inode and hard link to it. Okay. So for example, when you write on your terminal, echo something to the file, for example. So if you run this on your computer, file.txt, so this will create an inode for this file, okay? And the name of the file, which is file.txt, and this hard link. So you will create two things here. Okay. Hard link, which is the name of the file, and inode, which has the content of the file. And other attributes, not only the data. Okay. Okay, so we have the first sector of the disk, which is called master boot record. And this sector is used to boot a computer because here you have some system files which are used for running your computer. And the end of MBR contains a partition table, which table gives the starting and ending addresses of each partition. As I told you that via system, you can divided into partitions. And here we have a partition table of these after this block, which is stores all of this information. Okay, so boot sequence. So how the operating system runs on your computer. For example, we have a machine, we have a device which is called BIOS, and this BIOS reads in and executes the files that are found in the MBR sector. And this MBR locates the active partition, reads in its first block where the operating system is stored. And this is called boot block and executed it. The program in the boot block loads the operating system contained in that partition. Okay, so as I told you in the image that as you saw that we have a super block, and this super block we have here some like magic number to identify the file system type and the number of blocks in the file system and other key administrative information. So it's something like related to the file system, because here we have different file systems, different formats. And here you can, some information about this is stored in this block. Okay, so we have here various methods are used in implementing file storage to keep track of which disk blocks go with each file. Okay. So here, as you can see, how the files are stored in the file system. So here we have something like contiguous allocation, as I told you, contiguous, so in order, and linked list allocation, and we have inodes. So contiguous allocation stores each file as a contiguous run of disk blocks. So you know what's the meaning of contiguous? Contiguous will mean something like this. So one after another. So we don't have empty here. But if in case of random, so you will see something like this. So this is a disk. So one block is stored here, other block is stored here. No, this is not contiguous, this is contiguous, okay? Okay, so here we have some advantages of contiguous allocation. Simplicity, we need two numbers, only the disk address of the first block and the number of blocks in the file. So you can get all of the blocks of the file, right? So you just take the address of the first block. You take this address, and what is the number of blocks for this file? And you can get all of the blocks of this file, right? Read performance, and here read performance is better because they are stored in contiguous order. And this advantage, which is disk fragmentation, because here you have to store everything in contiguous order, which is not easy for the operating system. Okay, so here, for example, we have, as I told you, for example, we have something like file A, file B, file. So we have many files and they are stored in contiguous order. The state of the disk after files D and F have been removed. Okay, so we removed two files. So we have here empty spaces, right? Empty spaces between the files. So here we cannot store, for example, if we need some file to store some file which needs, for example, 7 blocks, we cannot use any of these empty blocks, right? Because here we need, because here we have to store them in contiguous order. But here we cannot, because here we have only 5 or 6 free blocks in contiguous order. Right, this is a problem of contiguous allocation. Do you have questions here? Do you have questions in this image? Did you get the point? Okay. Okay, linked list allocation. Linked list, it's the first word of each block is used as a pointer to the next one. Okay, here, as you know, that linked list, so we have data and we have a pointer to the next block, right? Here it's better something because here we can store them in not contiguous order, and maybe some random access could be, but here it's extremely slow, because here you have to read the pointer, because here you have to store them in linked list, right? So you have to read the first block, after that you read the pointer, the second block, the third, as like this. Okay, so here we know we don't have fragmentation, because here, yes, for example, here we have an example. So here we stored, for example, the first block of the file. After that, we have a pointer to the second block, to the third block, like this. Yes, and here we have another file. Okay. Okay. Okay, so here it's better than sequential. Why? Because here, for example, you can store the file with 7 blocks, right? So you store them, for example, in the 5 blocks, and after that you can store 2 of them in the one of these in 2 blocks of these 6 free blocks, right? So it's better than contiguous allocation. Okay, some of the advantages, the table is in memory, lookup is fast, only data are stored in blocks. Okay, because here you need a lookup table to look for the first block, because here you have to store only the first block, the address of the first block, and you go through these pointers until you reach the end of the linked list. The disadvantages, a whole table must be in memory, which could be very big, right? So you have to store all of these information about all files in the file system in the memory. So it's not easy task for the operating system. Maybe your memory is not very big. For example, here it's 3 GB. Nowadays, we have memory more than 3 GB, but we are talking about in the past. Okay. Okay, so here a linked list allocation. Yes, okay, so here file I starts here, file B starts here. Okay, so here you can see how this table could be in case of linked list. Okay, so what about inodes, which Linux operating system nowadays using them? Okay, inode is a data structure that's associated with each file, which lists the attributes and disk addresses of the file's blocks. Okay, so everything information about the file is stored in the inode, which is a unique, or you can say index number of the file. And when you create a file, you are not creating only inode, you are creating inode and hard link to this inode. Okay. Advantages: only inode for a file which is open must be in memory. Yes, because here, for example, if you have many hard links for one inode, and when you change something in one of these hard links, you will see this effect on other hard links, because you are writing on one inode. So let me show here some example. So if we have, for example, here we have inode, and here you created a file, name it file.txt, file2.txt. So you created 2 hard links. They are referring to the same inode. Here we have some number. Okay, but we don't have only number. We have information about the file. And here you can see, when you change this file, for example, you have this file in some directory, in this directory, and you change this file, and you go to this file, you will see the effect, right? Because they both refer to the same inode. Okay, so in the disk we are storing the inodes, but these file names are just hard links to them. Okay. Yes. Inode what? Yes, you will see it, because it's stored in the beginning of the disk, because you can reach them as quick as possible. Okay. Yes. Not same memory. You mean same? Okay. You can create on the same folder. You can create two files in the same directory, but they refer to the same inode. This was your question or different? Yes. 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 How? In the lab. Okay, you will see in the lab something like this. Okay. So here we have advantages like only inode for a file which is open must be in memory. Okay, requires an array in memory whose size is proportional to the maximum number of files that may be open at once. Okay, so here we have, for example, inode, address of disk block 0, address of the, so we have, for example, 7 blocks for the file, and we have, and here all of these addresses are stored in the inode. But we don't have only address, we have other things too in the inode. Okay, so when a file is open, the operating system using the path name supplied by the user to locate the directory entry on the disk. The directory entry provides the information needed to find the disk blocks. Depending on the systems, this information may be the disk address of the entire file with contiguous allocation, the number of the first block, both linked list schemas, or the number of inode. Okay, so here what we are talking about, it's how when you open the file, how the operating system interprets these operation. So first we are giving the path. After that, it will locate the directory that's stored the file in. After that, it will something like find some information needed to find the disk blocks. And after that, the information may be the disk address of the entire file. Okay, no. Okay, 10 minutes break. No. But please return at 10:13, okay? Okay. Hello again, everyone. Guys, are you ready? Okay. Let me continue. Okay. So here, when you open some file, so the operating system use a path, okay, to locate the directory entry on the disk, because this directory entry contains some information in order to locate the blocks of the file. After you find the disk blocks or the blocks of the file, because these blocks could be, as I told you, so there's something like contiguous allocation, linked list allocation, or I know. So it depends. Okay, so here we have some example for some directory entry. So here, for example, you see 3 directories. So we have here some information that could be stored in order to get the blocks of the file. And here we have a problem with long file names. So here, if we have long file names, so we have 2 ways to implement them. One of the ways is just to store the name of the file after the information of the file. For example, in file 1, so you see here, we have file 1 entry length, file 1 attributes. After that, you store the name of the file, okay? But there's another way of handling this issue, which is storing them in a heap. So you just keep the pointer to the file name and you store the files in a heap, which could be, as you know, dynamic size. It's not fixed size. What about shared files? So as I told here you that we can create 2 hard links to the same inode, which is shared file, right? For example, here we have some file which is shared between 2 directories. For example, you create 1 hard link and you put it in 1 directory, and you create another hard link, you put it in another directory. But they refer to the same file. When you change in one of these hard links, I mean the file, it will be changed in the other directory too. So it's a shared file, right? And here, for example, you see we have owner C, okay. And after here, after we make it shared, like, so you see here the count, it's 2, sorry. What's the count here? Do you know? What is the count refer? What the count here, the count parameter, to what it refers? Ah, yes, number of hard links. For example, here in the first case, we have only 1 hard link because we created 1 file in 1 directory. And after that, we created another hard link to the same file. So it's a shared file, but we put this hard link in another directory, okay? So here you can see 2 directories, B and C, and you put another hard link to another directory, so you will get count equals 2. And all of this information, you can get them using some commands in your terminal, and you will see them in the lab. Everything, implementing or anything else like these practical things, you will see them in the lab, okay? Okay, so here after the original owner removes the file, you can remove or delete the hard link, but the other hard link will stay, will remain, right? So how can I remove the inode? Do you have any idea? How can I remove the inode? So I created a file, it created inode and hard link. Ah, delete the file, maybe. But how to be sure that there is no hard link for these files that you are deleting? No, you have to search for all hard links of the file, right? And there's command which is fine, and you will see in the lab. So you have to remove all hard links to the file in order to remove the inode from the disk. Okay? Yes. Okay, maybe it's a mistake. Okay. For example, here we have a file system, Unix v7. So here we have inode number and file name. So you can imagine as a file name, it's a hard link. Okay. So here we have Unix. Okay, we have here some what is stored in the inode. So here you can see some like blocks, pointers to blocks, stored some attributes. So this kind of organization, how these blocks are organized in case of inode, because here, as you see that we store in the inode the addresses of these memory blocks that belong to the file. Okay. And here it could be stored different way because it depends on how it's organized in the operating system. Here's one implementation. Here, for example, we have example for this, we have 4 directories, 5 directories, and after that we have inode for directory user. And as you can see, so here we have some information, and then after that block 132. So it is another information pointer to this block. And after that, you see that another directory, for example, user ist. So we have another block, which is for the directory. So this kind of organization for files inside directory. Virtual file system. Okay, so so here virtual file system. It's kind of okay. Okay, here the virtual file system is kind of, you can imagine it like a cloud. So you have different kinds of, for example, operating system and or different kinds of file systems. And this virtual file system, it manages all of these heterogeneity among these file systems. Okay. Okay, here, for example, if you would like to store some data in the disk, but you need some free blocks, right? So here you see that we have addresses of the free disk blocks, and it's stored somewhere in the inode and not inode, sorry, in the directory entry. But here we have also the bitmap, and we will talk about the bitmap. Yes, after this slide. For example, here we have this quota, and this quota is about how the administrator it assigns some kind of flies and blocks. For example, you can, for example, create how many files, how many directories in the file system. And all of this information, it's stored in a table with kinds of attributes. Okay, about file system backups. So here we have some reasons why we need some backup to recover from disaster, to recover from something else. Okay, so backup takes time. Okay, first, should the entire file system be backed up or only part of it? What do you think? So this is not something like I can say. The answer is with you. So because here we don't have something like we don't mean something like from the textbook. No, it's just question to you. So we need to back up everything or just some personal data, for example, right? Because here we can install the program. And when you install the program, okay, so you can return everything, but personal data you cannot return it if it's removed. So you need to back up it. So here we have some information about backup. Okay, so here let me, okay, I think, okay. So here we have a dumping, logical dumping algorithm. This algorithm, so imagine that you have a tree of files here with directories, and you change some files. By the way, there's a mistake here in the file number 31, so it should be not changed, right? So the colored files and folders are changed, are modified. So we have to dump them, to write them on the disk, okay? So this algorithm, which is dumping algorithm, so it works in 4 phases, okay? First, it marks all of the changes. So I mean, in which inodes, for example, here we have 3, 2, 8, 9, 7. So you can see here, in the directory 7, we didn't change it, but we changed the files inside the directory. So it's changed, okay? Because here, when you change some file inside the directory, so you have to mark it as change it to, okay? So first of all, so you have to mark everything that's changed. In the second phase, you have to unmark. You have to unmark everything that's not changed, because the status of this bitmap could be from previous state. It's different, so you have to unmark everything that's unchanged. After that, you dump first the directories, okay? After that, you dump the files. This is the order, okay? Okay, about file system consistency. Okay, some information. Okay, so here we have some status for the file consistency. For example, here, as you can see in the first figure, so the file system is consistent. So here we have some of the blocks in use and some of them free blocks. But when we have some free blocks and the operating system doesn't reach it, so it will be something like missing a block in the disk, right? So the number here will be 0. If it was 2, now it's 0. Another situation, which is about when you have duplicated free blocks. For example, you have 10 free blocks in the disk, but you are getting information that you have 11 free blocks. So we have a duplicate. So in this case, the file system is not consistent. So there is something like handling of this situation. And the last state, which is about blocks in use. So we have duplicate blocks. For example, when you have when you have a file with 5 blocks, but you are reading 60 blocks. So you are reading 1 block duplicate. So in this case, the file system is not consistent, so it should be handled, okay? About the performance of the file system, okay, reading, okay, because here the information it's for HDD. Nowadays there's SSD, which is very fast, right? Because reading from the disk is not very quick, it's slow. Yes, and here the buffer cache data structure. So here, for example, the disk, there's a buffer, because here, if we read from the disk, because why we need from the disk? We need some information. For example, if you store something in the swap area, so you read it to the physical memory in order to run or to execute some process. And here, for example, we have some cache which is stored only the recent data to reach them, to access them quickly or as quickly as possible. Okay, here one of your classmates has asked about inodes. So here you can see the inodes. It's stored near the start of the disk. Why we can't reach them? Because here it's better to store the inodes in the start of the disk, because it will increase the performance of accessing these inodes, right? Okay, so let us talk about defragmenting disks. So you know what's the meaning of defragmenting? Yes. You mean blocks of the file. Okay, we didn't get it anyway. Any other answers? What's the meaning of defragment? This is defragment. Who is speaking? Who is speaking? Okay, okay, I don't see you. So why we need defragment? A long answer and yeah, an answer. Okay, anyway. So the fragment it's important because here when you defrag as a disk, so the blocks are stored in a contiguous order. Because here, whenever you find empty blocks or empty space in the disk, so you store the blocks. So the blocks of the file will be stored in different places. They are not in contiguous order. So accessing these blocks, because here we need to access them in sequential order, right? So accessing these blocks, it takes time because you have to search for all these blocks of this file in order to read them in sequential too. But if you store them in a contiguous order, so reading the blocks doesn't take so much time. Okay, that's why defragment is important, but it will take time if you run it, for example, on your operating system, because it will move the blocks in the disk in order to arrange them in contiguous order. Okay, so here we have some directory entry, and here you can see the file name where it's stored. We have some bits for attributes for extension, reserved, and for the time and date, and first block number. And here we have some block sizes, and here we have some formats for the disk, but they are very old, right? Because here we have NTFS for the Windows, and we have XT4 journal for the Linux. Okay, I think we've finished. Okay, and there are other additional material. If you'd like to read them, it's up to you. Okay, do you have question? Oh, okay, let me return. Okay, and yes, do you have question? Guys, do you have question? Yes. Not empty, but it's not shown for you. It's hidden now, we will show it, so don't worry about it. Huh? No, just, okay, now we can display it, don't worry. Any other questions? By the way, if you check, because here some information, it's not very recent information. Some, for example, HDD. So here we are talking only about HDD, but it's better to search for SSD, for example, because here the access of the data blocks is not very slow in SSD, it's very fast, right? Because it's like RAM. So accessing RAM is very fast, and SSD is very fast too. So it's better to search for them and learn about them information. And also about the new data partition formatting. So here we have, for example, FAT, which is very old, and nowadays you have NTFS, you have some other XT4 for Linux. It's better to learn about them on your own. I finished. Okay, so we can finish, right? Do you have anything to add, guys? Okay, so you can go if you don't have any question. If you have a question, you can stay and ask. Okay. Thank you.